What unifies everything and everyone everywhere? This question has baffled physicists and scholars for centuries. Nobel Prize winner Albert Einstein came up with the most respected physics equations, but his dream of finding the unified solution eluded even him. Where should one look for the answer to this universal puzzle? To the past? The future? The ends of the cosmos or beyond? Or inward? Is the answer inside a particle? A proton? Does our consciousness affect the nature of reality? Maybe clues have been left for us throughout the centuries, encrypted in sacred icons and symbols. Who among us can unravel the mysteries? Einstein was a technical assistant at the patent office when, in his spare time, he cranked out some of the most remarkable theories. Theories that remain the crux of classical physics today. Einstein once said, "Any intelligent fool can make things bigger and more complex. It takes a touch of genius and a lot of courage to move in the opposite direction." You expect a physics mastermind to be holed up in a big stone building with ivy crawling up the walls, not on the ski slopes of British Columbia, or swimming with the dolphins off the big island of Hawaii. Scuba diving and exploring the Bimini Wall near the Bahamas, or scaling the rest of the physical world, literally and mathematically. Nassim Haramein was born in Geneva, Switzerland in 1962. Like many other savants, this imaginative child frustrated teachers to the point he was ostracized. Few around him knew of the equations, mathematical quandaries, and probabilities that consumed his mind. As a young adult, Haramein spent months living alone in a van in California, tackling these nagging concepts until he met believers who supported his efforts.
This is our entrance to the laboratory.
Haramein struggled for the next 25 years working alone and with world-renowned physicist Elizabeth Rauscher, testing and finally potentially solving Einstein's dream. This lifetime of decoding started in 1972 when a teacher sparked Haramein's faithful inner journey.
This all kind of started when I was about 10 years old, and I got in my first geometry class. It was an exciting time because the teacher went to the blackboard and made a little dot and said, "Today we're going to learn about dimensions." When he said dimensions, I got all excited because I thought, oh, he's going to talk about all these worlds I live in my mind and all these other things I'm experiencing. I thought, wow, that's the first adult that's going to talk about that. And so I got really excited, and then I got really, really, really disappointed because after he put the little dot on the blackboard, he said, "The dot is dimension 0 and it doesn't exist." And I thought, oh, I think I'm gonna fail this class because I could see a dot from all the way in the back of the class. So if I could see it, how is it that it didn't exist? Then he did something even more miraculous. He put a bunch of dots together to make a line, called it dimension 1, and said that didn't exist either because it still didn't have volume. Then he put 4 lines together, made a plane, called it dimension 2, said that's the dimension that our comic strip books live in, and he said that doesn't exist either because it still doesn't enclose volume, it's flat. The teacher then did something remarkable. He took 6 of these non-existing planes, put them together into a cube, and said, now the planes enclose volume. This is dimension 3, and that's the one you exist in. And I thought, wait, how's that possible? I don't care if you have 1,000,000 non-existing planes. If you put them together, you still don't have existence. That didn't work for me. I thought, if the dot doesn't exist, the line doesn't exist, the plane doesn't exist, you don't have existence. Eventually I found out many other people found the same problem when they were young and were taught these axioms. One of them was a famous geometrist, Buckminster Fuller. Well, turns out that this fundamental axioms about geometry is some of what most of our math and physics is based on. Our physics and advanced physics, Einstein field equations, quantum theory, all this is based on flat space. And if these axioms, if this fundamental concept is not correct, then most likely what we're going to end up with when we run all these physics and all these mathematics to understand our world is going to be a little tweak. It's not going to be quite correct. So I didn't know all this at the time, at the age of 10, but certainly I wanted to understand it. I wanted to find a new solution. I had a long bus ride going home, and I thought, I got to figure this out. I was in the bus, and I was thinking, I'm not going to get out of the bus until I got this figured. I didn't know that many philosophers and scientists had grappled with this problem. I closed my eyes in the bus, and in my mind's eye, I visualized myself seeing the bus from above, and I rose further and further, and as I did, the bus started to look like a dot. And then eventually, I rose further, and the country I was in started to look like a dot. And I rose further, and I saw the Earth starting to look like a dot. And I rose further, and I saw the solar systems looking like a dot. And I rose further, and I saw the galaxy looking like a dot. And I thought, oh my God, it's dots all the way up. And then I flew back into the galaxy, flew back into the Earth, and found the bus I was in, and opened my eyes and looked at my hand, and I thought, wow, I wonder what's in my hand. And I closed my eyes again, and I flew into my hand, and I thought, wow, it's made out of millions of dots, cells. And then I flew onto the surface of one of those cells, and I looked around, and it was made out of millions of smaller dots that looked like stars in the sky. And I thought, whoa. And I flew into one of those dots and looked in the middle. Sure enough, there was another teeny-weeny dot in the middle of those atoms. And I thought, wow, it's dots all the way down. And a light went on, and I thought, oh, the way to solve the dimensional problem is to reverse the axiom completely and say the only thing that exists is the dot. Within the dot is infinite amount of division, infinite amount of information. And I thought, wow, everything is made out of dots, and the dots are arranged differently, and that makes up our whole world. I opened my eyes, and I looked at all the people in the bus, and I thought, wow, they're all made out of dots, and I could kind of see the infinite dots of their existence. I got really excited. But then I started to realize through a few other experiences that, wait a minute, if it's infinite divisions, if it's infinite, how is it that we get finite structure? How is it that we get a finite boundary? How is it that we have finite systems with like infinities?
Haramein didn't know it at the time, but he was grappling with one of the biggest chasms in current physics. Einstein's theory of general relativity covers the cosmic scales and the relationship between gravity, time, and space. It predicts continuum to an infinite point of singularity, or a black hole. Quantum theory covers the smallest units in the universe and predicts finite and linear boundaries. The two theories are at odds, but Haramein believes both viewpoints are interconnected because everything big is made up of something small.
In general, we could define our society in two ways. We've got people that have a tendency to be very spiritual, and these people tend to think in terms of infinities, that infinite potential and all this stuff. And on the other hand, we have scientific people that tend to think in finite systems, closed systems that have very defined boundaries. And the two don't necessarily agree. And I think that at this point, this has to come together. And in a very simple way, I'm going to show you geometrically that infinities and finite systems are actually complementary. If we take the boundary of a circle and we define that as our finite space. Now that circle could be a sphere. And we divide that circle so that a triangle is formed in it, an equilateral triangle in this case. Now the universe is polarized. Everything in the universe seems to spin, so spin produces polarity, so we would have a reverse triangle at the same time. As soon as we do this, now we've created a new boundary condition at the next fractal level down, the next iteration down. Now notice that these new boundaries all are centered around a very specific center. That is, each of the boundary defines a very specific structure in space-time, a very specific coordinate in space-time. And so each of the boundary could be defined as a very specific set of information. Now I can continue to divide the space to produce new boundary conditions. Now I've got another iteration down and another set of information. Now I can continue to do this and create new boundaries again. And at this point, you can imagine that if I give this to my computer, it could zoom in, bring it back up, continue to divide the space, zoom in, bring it back up, continue to divide the space, and it could do this to infinity. However, I would never, ever, ever, ever exceed that first boundary I've produced for myself. So here, I've embedded infinite amount of divisions, infinite amount of information within the confine of a finite space. So in very simple terms here, I've shown to you that infinities and finite structures are complementary. That within the confine of what appears to be a finite space can be embedded infinite amount of information. And if this is true, this simple concept could change all of our concepts of physics, including our concepts of our relationship to the universe. So why is that true? Think of yourself as made out of cells that are made out of atoms. Now there's about 100 trillion cells in your body and billions of atoms per cell. And imagine that all these cells and all these atoms can be further divided into subatomic particles that can be divided into subatomic particles and so on towards infinity. That would mean that you actually, even in your physical body, have a function of infinity. That is, you have an infinite nature within the confine of what you call the physical world. So you don't need to even have a spiritual concept of your infinite nature. It's actually the way you're made, if this is true.
This complementary fractal condition could change the fundamentals of physics. Quantum theorists adhere to a concept called the God particle. If we look hard enough, they believe, we'll discover the smallest division that the universe creates. Here's another way to approach it.
At first, when we had our first microscopes, when we saw cells, we thought, oh my God, those are so small, they gotta be the smallest thing the universe does. And then we found that those cells were made out of atoms. And the atoms are so small, we thought, oh, those are gotta be the God particle. Those are the smallest thing the universe does. And then we found that those atoms have nuclei in the middle, protons, neutrons, and those are teeny, weeny particles compared to the size of the atom. The universe goes all the way down to that size and then stops and says, okay, that's small enough, I'm not doing anything smaller. However, then we found quarks and so on. And at this point, we're building accelerators that are enormous, an extraordinary device that accelerates particles at faster and faster rates to get smaller and smaller particles, thinking every time that we're going to find this fundamental particle that can no longer be divided. However, every time some physicist somewhere write a new equation saying, oh, maybe there's another energy level, da 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 da, and then next thing you know, we're building a larger accelerator to try to find it. And now we're looking for things that are billions of times smaller than an atom. But based on this concept that we've just learned about, we would know that this can be done to infinity, that you can always get a smaller and smaller particle if you could get a larger and larger accelerator. So what is this really telling us about the universe? I think that a more worthy exploration would be to stop looking for a fundamental particle and start looking for a fundamental pattern of division. Because if we could find a pattern in which the universe divides, then we would have the key to creation. And that could be really useful. My first sponsors wanted me to spend a lot of time, interacting with other physicists to try to get some support from them and as well discuss ideas and see where my theory related to the mainstream and so on. And so eventually he dragged me to a bunch of different physics conferences, and I wasn't so excited because I already had a bunch of run-ins with the mainstream scientific community, and I was a little worried. But eventually, I got into this private conference at Georgia Tech, and we were discussing very advanced physics, string theory, there was equations everywhere, and so on. And I was kind of irritating people a little bit because I kept on asking fundamental questions. The only book I had brought was this book, Gravitation. Gravitation is the Bible of relativistic equations, and it's written by giants of physics, Wheeler, Thorne, and Mesner. And it has all the equations that describes relativistic equations and curvature of space.